Talk about Lecture 1, Modeling and Simulations. Just starting out with the definition here. Modeling and simulation is simply referring to the physical and logical representation. Physical and logical representation of a system. Representation of a system. So this is used to generate data. Once you have the data, you can do two things that are very significant. You can make decisions. You can make decisions and predictions. So that's modeling and simulation. It's just having a physical and logical representation of a system to generate data that will help you make decisions and predictions. Now, it's important to know what a system is. A system has quite a broad definition. It's simply components that have a purpose, components that are related and that have a purpose. That's a system. So it can be as simple as a waiting line, a queue. So this can be at a grocery or supermarket or bank. And the reason a waiting line can be a system because it has components, which are people that have a purpose. They're waiting in line for, the checkout, or they're waiting in line at the bank. And this is quite simple. But you can also have something as complex as an airport. That's a system as well. Now, in order to understand a model, so you have a model, right? You have a system. In order to understand this system, scientists make models, system models. So you can make system models to try to understand how the behavior of the system works. Let's take a look at the types of models. There are 4 types of models. The first one is a physical model. A physical model is quite self-explanatory. It's simply like a car or an airplane. Very simple stuff. Now, a visual model, on the other hand, is graphs and charts and stuff like that. So we can make a chart here to kind of have a visual component as well. And third, we have the mathematical/analytical model. And these ones have to do with variables that are connected to each other. So we can just make a cube here, for example, and we have a lot of numbers and variables like x equals 7 and y equals 3. So that's a mathematical model. And finally, we have the last one, which is a computer model, which is just simply made on a computer. So we have a computer here. It's simply made on a computer for calculations and predictions. Those are the 4 types of models. Now, what's more important are the characteristics of models. For example, if the model has randomness, then it's a stochastic model. Otherwise, it's deterministic. A deterministic model brings the same results every time. So, deterministic model has the same results to the same specific set of values. There's no randomness. Let's get this. It gets the same results every time. Now, on the other hand, stochastic models, they have different results every time because they have randomness. And it can be a small amount of randomness or a large amount of randomness, but however, you're going to get different results every single time. There's no variation in deterministic models. Let's move on. Now, if your model has time as a significant variable, so time is important. For example, if you have a bank, then time is important in that simulation. When the bank opens, when the bank closes. But if you have something as simple as a coin toss, well, time isn't a significant thing. We just want to know the results. If time isn't significant, then that's a static model. So this can be So time, not important. It's simply not something that is useful in the model. And this can be a coin toss. Now, if time is important, then that's a dynamic model. So time is important. And as I mentioned earlier, we have the example of a bank that opens and closes. So time is a significant part of that simulation. One type of simulation that at a point of time, so static, there's a specific type of simulation. It's called the Monte Carlo simulation. The Monte Carlo simulation. But it's not specifically related to coin toss, but it's a type of simulation that's static. So if you have the same set of variables, time. If time is not a particular importance in that simulation, then you can use a Monte Carlo simulation, and it could have randomness, it could not have randomness, but the important part is time doesn't matter in that type of simulation. Now, another characterization of models has to do with whether it evolves continuously or only at certain points of time. Now, if it evolves continuously, then it's quite intuitively called a continuous simulation. So it involves, for example, if you're tracking the water in a bucket, for example, if in a lake, the amount of water in a lake, for example, it's increasing every second or decreasing every second or something, or for example, stuff that just has continuously changing things. For example, and there are also properties in you can kind of understand with examples like temperature. Now, temperature is a continuous variable because you can have 40.0, 40.1, and something in the middle, 40.05. And you can continuously kind of make it, cut this in half, and you can have very specific and precise variables and values. So that's continuous. Now, discrete, on the other hand, is stuff that doesn't have an in-between. So, for example, you have the number of pages in a book. Just the pages in a book. Pages in a book. Now, one thing to notice is something like a tricky question could be: is shoe size a discrete or continuous variable? Now, shoe size has, like, for example, 5.5 or 7.5. So it has the decimal points. However, it's still discrete because you can't have an in-between. Once the shoe is made, there's no in-between in it. So yeah, shoe size is actually a discrete variable. So you can have 5, 5.5, 6. You can think of it as a measurement and not as a measurement, but as something that's precise. Not precise. So discrete is not precise. It's just 5 and then 5.5. But however, something that's continuous, it can be 40.00000 or 40.005, stuff like that. So this shoe size is a tricky one, kind of, in this characterization. Now, the next important thing we need to know is a discrete event simulation, a DES, a discrete event simulation. Now, this simply has changes at a point of time. So you have 1, 2, 3, and so on. And each one of these is an event. So this is an event, this is an event, this is an event, this is an event. So this can be like a customer walks in, and this can be when the customer leaves. The customer leaves. So this is important when you don't want to continuously simulate, as we talked about earlier, because that can be difficult on the process on the computer, and it's also not significant what's happening in between. So when the customer walks in and when the customer buys something, when the customer buys something, it's not important what's happening in between. We only want to know what's happening at these specific events. So that's why a discrete event simulation is important in that way. Now let's try to understand what simulation has, like where simulation is as a field of study. So there are three important fields of study that concern simulation. So let me just draw a Venn diagram here, if I can. So the first field is the application field. The second field is the mathematical field, and finally it's, of course, computer science. And here is simulation. It deals with all three fields: application, the application field, the mathematical field, and the computer science field. Let's take a look at when to use a simulation. Like, what are kind of the advantages and when it's important and helpful to use. And a simulation. So when to use simulation. Essentially, the most important points here is when it's dangerous, the system is dangerous. Dangerous system. So this is when, for example, you have a system that's difficult to kind of deal with and interact with. So you want to put it on a computer and try to understand it there, so you don't have to get harmed or anything. And also when it's difficult to influence the system, when it's difficult to observe, like if it's impossible, you could say impossible to observe or influence. So that's one time you can use a simulation, when you can't actually affect the system. And if you want to optimize a design or kind of look at the effect of a change, that's also when you can use a simulation. And here, this is why these are the advantages right here. Here's the thing: it doesn't interrupt the real world. It doesn't interrupt the real simulation, the running system, the real system. And it also doesn't consume a lot of resource. I mean, of course, the computer and the hardware is going to be a cost, but it doesn't consume resources in the same way, not even close to the same amount if you were to actually try it in the real world. So it doesn't consume resources in the same way. And with simulations, you can test hypotheses, you can ask questions, you can change the variables. So that's where simulations are really helpful. Of course, there are difficulties and downsides to simulation. So you can have disadvantages of simulation, which, for example, it's specific solutions, not general solutions. So sometimes you only get it for that set of variables that you've entered. So that's why it's difficult to kind of get a general idea. It's also time consuming, so you need time. It's time consuming to kind of understand and really understand and change the variables and try to get some data from it. So that's going to take some time. Obviously, you need memory, and so we can call that like hardware, for example, hardware. So you need the proper hardware to actually simulate. Of course, you need experts in this. So you need experts of the fields. And as I mentioned, the reason you need experts is because the results are complicated. Results are complicated or complex. And of course, it's expensive. Hardware is expensive. Software is expensive. And that is pretty much the way that's pretty much lecture 1. Of course, we can also take a look at this chart here. So we have system at top. We have what we can do to try to understand the system is to experiment with the actual system, or we make a model. So you can either make a model or you can interact with the actual system or experiment with it. Obviously, a lot of people are going to choose model, as we discussed what the advantages are when to use it. And you can either make a physical model, so a physical model, a 3D model in the real world, or you can make a mathematical model, one that is based on math that can be on a computer, for example. And then from math we branch out to either analytical or a simulation. And analytical can be mostly about the variables and taking a look at just numbers, while a simulation can have more of a 3D effect kind of. So that's pretty much it for lecture 1. Thanks for watching.